Suppose we have a situation like this. There's a bowl and there's a ball kept at the center. Now if we are going to push this ball is going to roll a little upward and then going to come back. And if we are going to do the same on the other side, it's going to go upward a little bit and then come back. We give a nudge on both the sides in all the directions, is going to come back on the same point. Now this kind of position is called stable equilibrium. It is an equilibrium because it is at rest, and it is stable because any disturbance is actually mitigated naturally and the ball comes back to the original position. So if there is a tendency to come back to the same position, then that equilibrium is called stable equilibrium. Now as we can see, why it is a stable equilibrium, because the potential energy is minimum at this point, and as we work we increase the potential energy, and if we remove and let it go, it will come back again to decrease the potential energy. That we can intuitively understand. Now mathematically, let's see. This is potential versus displacement graph. The ball is actually physically kept at this point, at this displacement. So considering this to be 0, considering this point to be 0, or any conveniently will take this to be 0, at which displacement is 0, the potential energy is minimum. Okay, now if you move this ball to this position and let it go, then what will happen? Let's see what will happen. At this point, the slope, we had a long discussion, and this should be very easy for us now, that at this point the slope, the tangent to the curve, the slope is positive. The tan theta, the angle which tangent is making, the tan of that angle is positive, the slope is positive, dy by dx is positive. Now, if that was y versus x, if you have u versus x, then du by dx will be positive. So, du by dx is positive at this point. This is very easy for us now to understand. Okay. Now, from the previous discussion, the one previously we have done was force is equal to negative differential of potential energy. We saw this. Now, from here we can see that the potential, the du by dx at this point is positive. That means the force is negative. Now, if we are considering this to be the positive direction, displacement, if this direction is positive, then force is negative. That would mean that force is in this direction. If force is in this direction, that force is going to bring this body back here. Similarly, if you have pushed the ball to this point, then tangent at this point is making an obtuse angle with x-axis. That means tan of that angle is negative. That means slope is negative. That means dy by dx is negative. That means du by dx at this point is negative. Du by dx at this point is negative. If du by dx is negative, then force is positive. And we have considered this to be the positive direction of displacement. As per sign convention, this is the positive direction. If this is the positive direction, then force is acting in this direction because force is coming to be positive. The sign is coming out positive at this point. If force is positive, then it's going to cause the movement of the body in this direction. So automatically the body will come back here. If it crosses this point, the force again starts acting towards left. It comes back here. If it crosses this point, the force again starts acting towards right. It comes back here. And after some time, it would settle at this point. So this is a stable equilibrium because on the right hand side, force directs towards left, and on the left hand side, force is directed towards right. So this kind of equilibrium would be a stable equilibrium. Now we have to encapsulate this condition into mathematical equation. Now we can see that this kind of thing will be true when the equilibrium is at the minima of potential versus displacement curve. When you have put a point at the minimum point of the potential versus displacement curve, then that point will be at stable equilibrium for the reason that we discussed just now.